Good day, my name is Trixie and I'm going to discuss normal spaces. So it is chapter 32 of the book of Moncrief. So all of the definitions, theorems, as well as the proof came from the book of Moncrief. So I do not own any of this. I just paraphrase, I just edit everything so that I can discuss and share it to you clearly. Okay, so for the outline or the overview, so I have two sections. The basic concept of the normal spaces, and the second one is the important theorems. So for the basic concept, I have included the definitions of the countable basis, Hausdorff, regular, and then of course the definition of the normal spaces. So I included those three definitions because it is very important in proving some theorems relating to normal spaces. And then I have included also three theorems, and then I have outline proof for that, so on how we can prove that. Okay, so the first definition, as I have said, so the countable basis. So what is countable basis? So according to the book of Moncrief, a topological space X is said to have a countable basis at X element of X if there exists a countable collection beta of neighborhood of X, such that every neighborhood of X contains at least one element of the beta. Okay, so the space isn't too big around any point, so you can describe all open neighborhood using only countable many building blocks. Okay, so I have also here an example. So it says here that the standard topology on the real number has a countable basis. So the beta is equal to the open interval AB, such that AB is an element of rational and where A is less than B. Since the set of rational number is countable, this collection of interval is also countable. So in short, a countable basis can be described all open sets using only countable many basic open sets. So for real numbers, the collection of intervals with rational endpoints is enough. So the real numbers has a countable basis. So this property is very useful especially later, so when taking or when talking about the normal spaces, because it makes the space manageable in size. So meaning, it is easy for us to count, or of course it is a countable basis, so it is manageable in size. Okay, next is the Hausdorff. So we have discussed the definition of Hausdorff during the class. So a topological space X is called Hausdorff space if every pair of distinct points x sub 1 and x sub 2 element of X with x sub 1 not equal to x sub 2, meaning they are disjoint, then there exists a neighborhood u sub 1 of x sub 1 and u sub 2 of x sub 2, such that the intersection of that neighborhood u sub 1 and u sub 2 is empty. So meaning they are also disjoint. So we know that in Hausdorff we have 2 points which is disjoint, and their neighborhood of that 2 points is also disjoint. Okay, next is the regular. So suppose that one point set are closed in a topological space X, then X is said to be regular if every point X element of X and every closed sets B subset of X with X is that an element of B, and there exists a disjoint open set U and B such that X is an element of U and B is a subset of V. And the intersection of the open set U and V is also empty. So they are also disjoint. So in the regular space, so we have a point and we have a closed set. So a point has an open neighborhood, and the closed set has an open neighborhood where that open neighborhood of X and the open neighborhood of set B is disjoint. So wherein X is not an element of the closed set B. Okay? And then, so now let us move on to the important definition for this topic. So the normal or the normal spaces. So a topological space is said to be normal if for every pair of distinct closed sets A, B, subset of X, there exists a disjoint open set U and B such that A is a subset of U and B is a subset of V. And the intersection of that open set UB is also disjoint. So we have two closed sets A and B, and that two closed sets A and B, they have an open neighborhood. So A has an open neighborhood U and B has an open neighborhood V. So wherein that closed sets are disjoint as well as their neighborhood is disjoint. So we see the difference between Hausdorff, regular, and normal. So when we talk of the Hausdorff, so we have 2 points that are disjoint, and also their neighborhood is disjoint. And in the regular, we have a point and we have a closed sets, wherein that point and closed sets is disjoint as well as the neighborhood of that point and closed set is also disjoint. And in the normal space, so we have two closed sets which are disjoint and their neighborhood is also disjoint. Okay, so it is easy to distinguish what's the difference between the three. So for a better understanding, I have here a simple example on how we find a normal space on a topology. So let X be equal to ABC and define on a topology of X by tau is equal to null A, BC, and X. Okay, so we know that the topology or the elements in the topology are open. So the complement of that open set is closed. That's why in getting the closed set, so we get the complement of open sets. So the null or the complement of the empty set is X. The complement of A is BC. The complement of BC is A, and the complement of X is empty set. So we now consider two disjoint closed sets. So for us to have normal spaces. Okay, so we'll let A to be equal to A and B to be equal to B. And we know that they have no common elements, so they are disjoint. That's why we say that A intersection B is empty. Okay, we can find disjoint open set U and B such that A is a subset of U and B is a subset of B. And the intersection of that open sets U and B is empty. So they are disjoint now. So we choose U element of U to be equal to A, where A is an element of the open set or the topology. So we know that U is an open set, so we have to find a open set which is neighborhood of A. So that is A, and then B to be equal to BC, element of topology. So we know that BC is open in topology or in tau. Then we can see that A is a subset of U and B is a subset of V. So their intersection the intersection of that open set is also disjoint. Okay, or empty. So since we have discussed the normal spaces, and then as well as we provide examples, so it is time to discuss, or in the part or the second section of this discussion, the important theorem. So I have here theorem 32.1, point 2, and then point 3. Okay, so for theorem 32.1, it says here that every regular space with a countable basis is normal. As you have remember, we have discussed regular space, we have discussed countable basis, and we also discussed normal. Okay, so now it is easy for us to discuss this because to prove this, because we already know the concept of the tree. Okay, so if we have, or every regular space with a countable basis, then it is a normal. So for our proof, we'll let X be a regular space, a regular topological space with countable basis beta, and we'll let A and B to be disjoint closed subset of X. So what our goal now? So if we have a regular space and with a countable basis, what is left to show is that it should be normal. So we have to find this joint open set U prime and B prime such that A is a subset of U prime and B is a subset of B prime, where U prime intersection B prime I empty. Okay, so how can we do that? So first, we cover A avoiding B, so that we will have an disjoint set wherein we should have A avoiding B, which means that A should be disjoint from B. Okay, so for each X element of A, we choose open set U, where X is an element of U, such that the closure of U intersection B is empty. Okay, since why is it possible? Because regularity ensures for each X element of A and close B, so there exists a disjoint open set and around X and B. Okay, so since X has a countable basis, we pick B sub X element of beta such that X is an element of B sub X subset of U. Okay, so we use basis element to get the countable collection. So now, we collect such B sub X into countable collection of U sub n covering A. So because the basis is countable, the distinct B sub X form a countable family. So that is each closure B sub X subset of U, the closure of U, so that the B sub X intersection B is empty. Okay, so we have now shown that the covering of A avoiding B. Okay, in the same way, so we now we find or the covering of B avoiding A. So of course B should be disjoint from A. So for each Y element of B, we choose an open set B element of where Y is an element of B, such that the closure of U sub n intersection A is empty. Okay, and then we choose a basis element B sub Y element of beta such that Y is an element of B sub Y subset of V. Okay, so the distinct B sub Y's form a countable collection B sub n covering B. So now we have an open set covering B, and then B should be subset of the union of B sub n, from n is equal to 1 up to infinity, and that is we have the closure of B sub n intersection A is empty. Okay, and then we now have an open covers A subset of A subset of the union of U sub n, where B is a subset of the union of B sub n. Okay, so as we can see, these covers are not yet guaranteed to be a disjoint yet. So while we find, or while we shown that both A and B are disjoint, but we are not yet sure that if that covering, or if that open neighborhood of A and B are also disjoint. Okay, so by ensuring that it is disjoint, so we modify to make them disjoint. So for each n element of a positive integer, we define u sub n prime is equal to the complement of the union of the closure of B sub I, where I is equal to 1 up to n, and we also have B sub n prime is equal to the complement of the union of the closure of U sub I from I is equal to 1 up to n. So we trim U sub n by removing the closures of the first n and B sub I, and then vice versa for B sub n. Okay, so we can see that U sub n prime and B sub n prime are open. So each U sub n prime contains a points A avoiding B, and the same way each B sub n prime containing points of B avoiding A. So this ensures that the new set will not overlap when we take unions. Okay, so this is the visual representation in the book, okay, of Moncrief, so on how that proof goes. Okay, so as we can see, the A and B, so these two rectangular shaded regions are disjoint and close. Okay, and then we have on the left side, we have U sub 1 and U sub 2, which is the open covering of A. And then on our right side, we have B sub 1 and B sub 1, B sub 2, and B sub 3, which are the open covering of B. As we can see, all of the open covering overlaps, so which we don't like, because the definition of the normal spaces, or it should be normal if the neighborhood is also disjoint. That's why we trim that. So this is the new collection. So these are the modified open sets. So after we trim them to remove the overlapping parts, as we can see now that the neighborhood of the closed set A, okay, and the neighborhood of the closed set B is not overlapping, so they are not now disjoint. So we successfully proved that if we have a countable basis, or if it is a regular with a countable basis, then it is normal. So for the step 4, it says here final open set. So for the conclusion, we can see that U prime is equal to the union of U sub n prime, where n is equal to 1 up to infinity, and then for B sub prime is equal to the union of the B sub n prime from n is equal to 1 up to infinity. Okay, so we can see that we know that the U prime and V prime are open, and A is a subset of U prime and B is a subset of B prime. So why they are disjoint? So if X is an element of U prime intersection B prime, then X is an element of u prime, and x is an element of b prime sub k for some j and k. So if j, okay, I have not mentioned, I'm sorry. So if x is an element of u prime intersection b prime, and then x element of the u sub j prime, and x is an element of uh, b sub k prime, then for some jk. So if j is less than or equal to k, then x is an element of u sub j subset of the closure of u sub j. But b sub k prime is equal to the complement of the union of u sub I, where I is equal to 1 up to k. So this implies that x should not be an element of the closure of u sub I, which is a contradiction. So it is the same as if j is greater than or equal to k. So that's why the open set u prime intersection b prime is empty, so they are disjoint. Therefore, x is normal. Okay, so for the next theorem, we have theorem 32.2. So every metrizable space is normal. Okay, so any space that can be described using distant function, okay, which is a metric, automatically has the property of being normal. That is, for any disjoint closed sets, you can find two open sets that keep them apart. So if x is a metric space, then x is normal. So our goal here is to just is for any two disjoint closed sets A, B subset of x, we find the disjoint open set UB such that A is a subset of U, B is a subset of V, and that the intersection of UB is empty. Okay, so to separate these two closed sets A and B using open sets that don't overlap at all, so this separation shows that the space between the space behaves nicely. So no two closed sets are too closed. Okay, so for the proof, okay, so we choose protective balls around each set. So for each A element of A, there exists epsilon sub A, which is a positive, such that that epsilon ball intersection B is empty. So it says it's like saying we take any point A in A, because A and B are close and disjoint, so we can find a small distance so that the open ball around A does not touch B. So similarly, for each B element of B, there exists epsilon sub B, which is a positive, such that the intersection of that epsilon ball intersection A is empty. Okay, so we just do the same for every B in B to make a little ball around it that avoids A. So we shield each set by open balls that avoid the other closed sets. So we think of this open ball as a like a protective bubbles, so that every point of A and B gets its own bubble that keeps it safe from the other set. Okay, so for the step 2, we define open neighborhood. So we define U to be equal to the union of the epsilon ball of where we have an A and epsilon sub A over 2. A is an element of A, and then we have B is equal to the union of that epsilon ball, where we have B and epsilon sub B over 2, where B is an element of B. So we take all the smaller protective balls around A and then combine them to form U, and do the same for B to form B. So these unions are open sets that cover A and B respectively. Okay, so each U and B is open, so the union of the open balls. So clearly, A is a subset of U and B is a subset of V. Okay, so since each ball is open and the union of open sets are also open, so both U and B are open. So because we build them from balls centered at a point of A and B, so then it contains those points. Okay, and then for the step 3, so we show that U and B are disjoint. So we assume that we assume for contradiction that there exists C element of U intersection B, meaning they are not disjoint. Okay, so we suppose that just to test that the two open sets overlap at some point Z. Okay, and then for some A element of A, B is an element of B. Okay, the distance between A and C is less than epsilon sub A over 2, and the distance between B and C is less than epsilon sub B over 2. So that means that C is very close to some A in A, also very close to some B in B. So by triangle inequality, so we know that this is true. So the distance between AB is less than or equal to the distance between AC plus the distance between CB, less than the epsilon sub A plus epsilon sub B over 2. So this shows that A and B are close to each other, closer than their original protective bubbles. So depending on which radius is smaller, so either A is an element of that epsilon ball or B is an element of that epsilon ball. So which is a both contradiction, because we pick a radii especially to make sure these balls do not intersect. So our assumption that C exists is false. So that means that C must not be an element of U intersection B for them to be disjoint. So which means that U intersection B is empty. So thus we have proved that every metric space is normal. Okay, so now let us move on to the last theorem. So theorem 32.3. So every compact Hausdorff space is normal. So we know that, or let us recall that a compact Hausdorff is regular, and regular plus compact is implies that we have normal. So we will prove normality directly using compactness and regularity. So we already know compact Hausdorff are regular, and this theorems goes one step further, combining compactness and regularity implies normality. Again, if we combine that, so we have compactness and regularity, which implies normality. Okay, so for the step 1, so this is the outline of the proof. So for step 1, so regularity of each point in A. So we let A and B to be disjoint closed sets. So we want to separate these two sets. So for each A element of A, since X is regular, there exists an open U sub A, B sub A, such that A is an element of U sub A and B is a subset of V sub A, where the intersection of V sub A and V sub A and U sub A is empty. So meaning they are disjoint. Because the space is regular, we can find two disjoint open sets around A and B. So for each point A, we can separate it from the entire set B. So the collection U sub A such that A is an element of A is an open cover of A. So this open sets U sub A together cover all of A. Okay, and then for the step 2, so compactness and construction of U and B. So since we know that A is compact, so we select a finite subcover. So A is a subset of A sub 1 or the union up to their union up to U sub A sub M. Because of the compactness, we don't need infinitely many U sub A, so we only need a finitely many which are enough to cover A. So we now define U to be equal to the U sub A union U sub up to the union of U sub A sub M. And then we have B to be equal to B sub A sub 1 intersection up to V sub A sub M. So we combine all those open U's to form big U sub U, and then we take the intersection of all B's, so to form a smaller B. So this ensures that both remain open and still disjoint. Okay, and then we know that U and B should be open, and U is a subset of A is a subset of U and B is a subset of V. So their intersection is also disjoint. So we have proved now that it is normal. Therefore, or hence, we successfully separated A and B, which with this joint open set. So therefore, every compact Hausdorff space is normal. Okay, so that's all for today, and I hope you learned something. Thank you for listening.